right, let's go over this test. All right, first section, sequences. All right, a sub n, 1 over n plus 1. In order for a sequence to converge, we need the nth term to have a limit as n goes to infinity. That's all we need is a limit. Any limit will do, as long as it's a real number. When you take the limit as n goes to infinity here, that's equal to 0. So that sequence converges to 0. Okay? Number 2, nth term, negative 1 to the n. Well, what happens with this, when n is 1, you get negative 1, positive 1, negative 1, positive 1, negative 1, etc. There is no limit. Therefore, diverges. This converges. This one will diverge. If there is no limit, the sequence diverges. A sub n is n squared over n plus 1. The limit as n goes to infinity here, okay, of a sub n is infinite, okay? Because the numerator is increasing faster than the denominator. These terms are going to go to infinity. Therefore, it diverges. Okay. All right, now we're doing sums of series. A series is a sum of these terms. The first one is geometric. Geometric means each term is multiplied by the same common ratio r to get the next term. R here is equal to negative 1/2. A is the first term, 1. As long as r has an absolute value less than 1, the series will converge and have a sum that's equal to a over 1 minus r. So a, 1 minus r, okay, 1 minus a negative 1/2, 1 plus a half, 3 halves, 1 over 3 halves is 2/3. If you have something wrong, but your work is essentially correct, let me know. It's possible to get partial credit. Okay. Number 5. We have a series, 1.1 to the n. This is geometric. But each term is multiplied by 1.1. 1.1, okay, is greater than 1. Therefore, the series will diverge. Okay. In order for a geometric series to converge, r must have an absolute value less than 1. Okay? These terms are increasing without bound. They're not heading towards 0. If the terms of a series are not going to head towards 0, it has no hope of converging. And this one will diverge. Number 6, we have what is called a telescoping sum. And I'm going to tell you, telescoping sum is on the final. Okay, you will have one of these on the final where I ask you about this here. Or is it partial fractions? I saw it. It's either the partial fraction one or the sum. It's probably the partial fraction problem. I think I lied. Okay, I just looked at the final and I saw there was a problem like this, but I think it was in the context of partial fractions. Find the sum of the constants a plus b, as opposed to one of these series. Okay, so.
Okay, in the end we just need to add like a plus b.
Yeah, that's all you have to do is find a plus b. Yes. Okay, that's all you're going to have to do. So, what did we do with this? We're going to do this. This is what you're going to have to do, is find a and b. You find a by multiplying through by n plus 1, and then let n equal negative 1. Negative 1 plus 2 is 1. A is 1. You find b by multiplying by n plus 2. Let n equal negative 2. b is equal to negative 1. Now, if this on your final, if I give you this problem, you have to find a plus b, which would be 0, and you'd be done. But here, you're going to have to set this up and find the sum of the series. Well, what happens is you're going to rewrite it now this way. And if you write out a bunch of these terms, you're going to end up with a 0 plus 1 is 1 minus 1/2. A 1/2 minus 1/3, a 1/3 minus 1/4, etc. These all cancel out. Okay. Now, if you go to k and let k go to infinity, that will go to 0. The only thing that matters is the one term in the beginning that's left, and that's equal to 1. Okay. That series has a sum that's equal to 1. Okay. All right, that's 6, 7. Now we're going to state whether the series converges or diverges. All right, first one, 1 over n plus 1. The difference in degrees, you're taking the denominator, its degree minus the degree of the numerator. That difference in degrees is 1. That's insufficient to cause the series to converge. This series will diverge. Okay? The difference in degrees is simply 1. If you had to prove it, you would prove it with a limit comparison test with the p series 1 over n. Or you could prove it with an integral test. The integral is pretty simple to do. You could do it that way too. The point is, difference in degrees is only 1, not sufficient to cause this thing to converge. It will diverge. 8. On the other hand, number 8, 1 over n squared plus 1. The difference in degrees is 2, which is sufficient to cause it to converge. You would prove it by a limit comparison test with the p series 1 over n squared, or even an integral test. You could do an integral test, get arctangent, and you would see the arctangent converges. 9. You have 10 to the n over n factorial. This is a case where you're going to use the rates of relative increase. Factorials increase faster than exponential forms. Therefore, these terms will go to 0 fast enough to cause the series to converge. If you had to prove it, you could prove it with a ratio test. And a ratio test would work rather nicely. And the ratio would go to 0 as n goes to infinity, meaning it does converge. Okay? Number 10. N equals 0 to infinity. Square root of n. Well, as n goes to infinity. Hey, Nick.
Hey, what's that?
I'm going over the test.
Yeah.
I talked to Chris. He doesn't want anybody to.
That's fine.
I kind of suspected that.
But yet he calls you?
He called me and I answered.
No, what I'm saying, but yet he calls you?
Oh yeah, he calls me. He calls me all the time, as you know. But he talks to my phone. He talks to me, I mean, you know, but he doesn't want somebody coming to his house. To his apartment, whatever it is.
I don't have to come to his house.
Yeah, I know.
If he wants
I
to,
said that.
We
He
can,
said
we,
he-
can, we can go like Mickey D's or something and just chill.
I know.
All right, that's fine.
I mentioned that.
Thank you.
Okay, number 10. Square root of n, the easiest way to see this is as n goes to infinity, the square root of n goes to infinity. Doesn't go to 0, therefore it diverges. Okay. If you put it over 1, you see the difference in degrees is not greater than 1. It's actually negative 1/2. If you take the degree of the denominator minus the degree of the numerator, you get a negative 1/2, clearly not greater than 1, which would what you would need to cause it to converge. But the fact of the matter is these terms are not going to 0, therefore this series will diverge. 11. We got a factorial over an n cubed. Factorials increase much faster than polynomials, therefore the numerator is increasing faster, therefore this is going to diverge. These terms are not going to go to 0, they're going to infinity. Okay? 12. N equals 1, 2 to the n over n squared. Again, we have an exponential function here, and we have a polynomial. Exponential functions increase faster than polynomials. Therefore, these terms are not going to go to 0. They will go to infinity. This will diverge. Prove it with a ratio test. Actually, you can prove that that limit as n goes to infinity is not 0 by using L'Hopital's. And that will show that this nth term does not go to 0. Hey, Vitali, how you doing? Did you take this test?
No.
Yeah, you need to take this exam.
I mean, taking the test.
What's that? Did you do this? Oh,
Yeah.
Here you go. I found it.
No.
Okay. 13. N equals 1 to infinity. Square root of n cubed plus 10. Difference in degrees, 3 minus a half, 2.5. Good enough to cause it to converge. Okay, 14 through 16. 14, alternating series. -1 to the n, square root of n. First thing you do is look at the positive series. Difference in degrees is only in 1/2. The positive series diverges. What that means is this series is not absolutely convergent, okay? But it could conditionally converge or it may diverge, okay? What do you do then? You look at 1 over the square root of n. You take the limit as n goes to infinity. That's equal to 0. Well, that's good. That's one part of it. The second part is, what happens to these terms? When n is 1, you get 1. That's greater than or equal to 1 over the square root of 2, which is greater than or equal to 1 over the square root of 3, which is greater than or equal to 1 over the square root of 4, etc. As long as the terms are decreasing like this and have a limit of 0, the alternating series converges. This is conditionally convergent, converges conditionally. Okay? The positive series diverged, but the alternating series converged. That was 15, right? No. 14, yeah, I was 14. Okay, 15. -1 n cubed. If you look at the positive series, difference in degrees is 3, converges. Therefore, the alternating series converges absolutely. Okay, converges absolutely. Okay. 16. N equals 1 to infinity. -1 to the n. We have n over n plus 10. Take a look at this, n over n plus 10. That's going to go to 1 as n goes to infinity, not 0. Therefore, it diverges. Okay? Okay, that diverges. Any questions on those?
Wait, 16.
Go ahead.
So the original was,
Right there.
that's the first one. Okay, so it automatically diverges because...
Because this is not going to go to 0.
Oh, because it's one, okay.
And that's, yeah, it's going to go to 1, so not go to 0. All right, 17. Find the radius of convergence. X to the n factorial. Take the limit as n goes to infinity. Absolute value n plus first term over the nth term. We want to find the x's that cause that limit to be less than 1. It's for those x's the series will converge. So, take the limit as n goes to infinity. X to the n plus 1, n factorial, this comes up top. Down below we have this x to the n, and we have the n plus 1 factorial. We can simplify x to the n plus 1 over x to the n, subtract the x1, so you get an x. N factorial over n plus 1 factorial is n plus 1. After all, n plus 1 factorial is n plus 1 times n factorial. As n goes to infinity, it doesn't matter what x is. As long as n is going to go to infinity, this is equal to 0, which is less than 1 for every x. Therefore, the radius of convergence is infinite. Okay? That converges for all real numbers. All right? All real numbers. This is the Taylor series centered at 0, the Maclaurin series for e to the x, which converges for all x. Yes?
How's R infinity? I'm not quite getting it. So if it goes to 0, that's understandable. So what is R?
R is a radius of convergence. What that means is, well, it doesn't matter what x is, this is always going to be less than 1. That says that this series converges for every real number x. That means x can go from negative infinity to positive infinity. And no matter what real number you stick in there for x, this will be less than 1. Therefore, the series will converge for all those numbers.
So
Therefore,
R equals x?
so R, no, the radius of convergence is from the center, which is 0, to either end. And the R says, start at 0, go infinitely in this direction, infinitely in that direction. That's what the radius of convergence is. It's the distance from the center to the endpoints. Well, there is no endpoint here because it goes on infinitely.
Okay, so R would equal 1. That means it'd be 1, negative 1, right?
Correct.
Okay.
Correct.
And where did you plug it? You would plug it in for n, right?
That tells you what x's cause it, what x's will, the series will converge. So this interval here says all the x's in this interval will have the series converge. These are for the x's. Okay. 18. This one may be clearer because there is a real number answer here. You take this series, x to the n over 2 to the n, okay? Do the same thing we just did. And flip it over. And simplify. X over 2. Now there's no ends. The ends have all gone away. What is this limit? It is the absolute value of x over 2. And what you can do here is take this 2 in the denominator and multiply both sides by that 2 to get the absolute value of x is less than 2. That means this is your radius of convergence, which means what? This series converges as long as x is from negative 2 to 2. It's centered at 0, goes 2 units this way and 2 units this way. Okay? That's what R is, that distance from the center to either endpoint. And it's always going to be balanced. It's always going to be symmetric with respect to the midpoint, okay, or center.
So if it was x over 1 and b radius of convergence, would it be 1?
You got it.
Okay.
That's exactly right. Okay, 19 and 20. Use the Maclaurin series for sine x. First two non-zero terms. Well, you should know that sine x is an odd function, and it's equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, 7th over 7 factorial, etc. What we're going to do is use the first two terms to approximate the sine of 1 radian. 3 factorial is 6, we get 5 6. Okay? That's our approximation for sine of 1 radian. What kind of error do we have? Well, the error is less than or equal to the next term. The next term would be 1 over 5 factorial, which would be 1 over 1/20. Okay. So we know how accurate that is. Okay, that's your test. Okay, any questions on that? We all set on that? Okay, I'll tell you what. Let me go over the topics for the final. Monday we'll take a sample final. I will correct it. If you do well enough, you can be gone. You can be done. Sayonara. Hasta la vista. whatever. Take the language of your choice. And if not,
Are this is the topic specifically that was going to be on the finals?
I'm going to give you the topics, yeah, right now.
You're just gonna give us some topics and, that's it for today?
I'm going to give you the topics that are on the finals. Well, it's hard to just, I'm going to tell you, I'm not going to tell you the exact problems, but I am going to tell you this. The first 8, I'm going to give you, I'll break it down by section.
Oh,
Okay, okay, here we go.
25 questions, if I'm fair.
25 questions, yes. Here you go.
Okay.
Fine. 1 through 8 is integrate the following. Now, these are integrals that we did in the first chapter. These are u to the n. Here, they're these. They're things like, I can give you examples. Okay. Well, first of all, dx. These are all definite integrals. Wow, every one of them. They're all definite integrals. Something like this would be on there. Okay. Here, let's make sure this thing here gets people. What's the integral of dx? Man, okay. Okay. Then you may have, there are going to be, some are going to be really simple. They'll be insulting to you, but don't be insulted. Okay? Very straightforward ones. The integral of e to the x. Okay? These kinds of things will be on there. These are the things we've done. Sine x. Okay? And they get a little bit more difficult. You may have an inverse sine, arc sine. You may have an inverse tangent. But these are those forms. And then you're going to have things like this. Yeah, go ahead.
We're going to have to, I remember on some exams we didn't have to go through the whole integral or...
You're going to have to. These 8 problems are all definite integrals. You're going to have to do the integrals out and get an answer. Okay?
These are just examples of...
Yeah, these are examples of the kinds of things you're going to see. These are the examples of the things we had in that first chapter.
Okay. If we go over the, if we look over the exams...
Oh, that's the best way.
That's the best way?
That's the best way. Okay? These kinds of problems. You'll notice the secant squared one, that's not from the chapter on the trig integrals. That's from the first chapter, where the integral of secant squared is tangent. We had that integration form from the first chapter. So these integral, no partial fractions here, no trig substitutions, no integral of sine squared or cosine squared in this first section. Okay?
So for the integration form, whereas 1 over square root of 1 minus...
Inverse sine, yes, that would be on there. You may have one of those, okay, to evaluate. Because that came from that first chapter.
Wait, inverse sine, what is that? That's inverse sine now.
That's inverse sine right here. What's that?
That's the answer.
Yeah, that's inverse sine x. And then I'll give you limits of integration here. Okay. Inverse tangent. I wouldn't even give you the inverse secant. That's just too obscure. Maybe I'll make a special test for Batali. I don't know. All right, but anyhow, that's the first section. Next section, 9 and 10. You're going to have a radioactive decay, population growth problem. One or the other. I think on the test that we have with that, I think I gave you one of each.
Is it population one?
A half-life, I could easily give you a half-life one. It could be a population growth where you have to find doubling time, that kind of a thing. It's going to be one or the other.
Can you do an example again?
You want me to do an example? Sure. Which one?
It doesn't matter.
Okay.
Well, can you give the equations for each?
All right, the equation for each radioactive decay, okay, you have Q is equal to Q sub naught e to the negative KT. That's the formula that's used for radioactive decay. Population growth is P equals P sub naught e to the KT. Okay? Now, what you're going to be given, I would give you the rate K. I don't know if I used K or R when I did this, but that's the rate of population growth here, K is, and this K is the rate of radioactive decay. I will give you that. I will give you an initial quantity,
Okay.
and I will ask for, say, half-life or doubling time.
Half-life would be just half the time, right?
It would be the time it takes, the quantity to go from what it started with to half of that. I could do one. You want me to do one?
Yeah.
Here.
do an example.
All right. Suppose Q sub naught starts off to be, what's that?
It was K.
It was K. Oh, good. Okay, good. All right. Let's say it's 100. I'd say it's 1,000 grams of radioactive material. Let's suppose the rate of decay is 10% per year. Okay. Radioactive decay. Just, I saw a debate with Bill Nye the Science Guy. Never mind that. Okay. But he mentioned this in there. Okay. So, Q is equal to Q sub naught E to the negative 0.1 T. That would be the equation for the amount of radioactive material Q at any time T. Okay? So if I ask you how much material is there after 1 year, you let T equals 1 and you do that. But I will ask for a half-life if I give you this problem. And what do you have to do then? Well, Q then is going to be 500. So let Q equal 500. And you want to solve for T. Well, divide by 1,000.
Basically, for half-life, we take half of the
Original.
Okay.
Yep. Yep. That's exactly right. So you get e to the negative 0.1 t. You want to solve for t. You want to get rid of this e. Take the natural log of each side. Take the natural log of this side. Okay. Natural log of e to any exponent is that exponent. Now, you end up with a negative 0.1 t. So you want to solve for t. You're going to divide by negative 0.1. So t is equal to natural log of 1/2 divided by negative 0.1. Now, I'm not sure. Wow, would I leave it like that? I would not leave it like that. Okay, here you go. I would expect you to know the following. Number one, the natural log of 1/2 is a negative natural log 2. Okay, everybody with me on that? Because that's 2 to the negative first power. The negative 1 comes out front. Or think of it this way. It's the log of a quotient, which is the difference in the logs. It's the natural log of 1, which is 0, minus the natural log of 2. You end up with a negative natural log 2. Now, that's over a negative 1/10. Okay. The negatives cancel. When you divide by a tenth, you multiply by 10. This is the answer I would have on the test if I were to give you this problem. Okay? So be careful. Don't get this wrong because you're looking at this and this is what the answer is. Okay? This here will not be on the test. This one will. Because this is the better form.
So you flipped over the half and made it negative,
Yes, yes.
which that's all you did pretty much. So anytime you have a fraction and it's in the natural log, you just flip it over.
Yeah, as long as the numerator is 1. Yeah.
Okay.
So if it was, say,
Go ahead.
2/3.
Natural log of 2/3 now. This is the natural log of 2 minus the natural log of 3.
I don't see it.
So that,
But see, you're not going to get that in this kind of a problem.
No, I just want to know.
Yeah, that's it.
So
That's what you would
obviously
get.
just subtract them.
Yep.
Then why is half like, oh, because it's minus 1? Zero. Okay. Thanks.
Okay, that's the radioactive decay problem. If you get the population growth problem, I'm going to be asked for doubling time. So, yes. What's that? Yeah,
yeah, there's.
I have some.
Table.
Oh, there's some on the table too. Here. There's a note here too. It's not to me. All right. Population 1, you'll get something like this. Initial population is something or other. 1,000 viruses, avian flu virus or something, which is making the rounds now. 10 billion chickens affected, I guess. But anyhow, let's say 1,000. You have a rate of growth of, let's say, 20% per hour. I would ask you for doubling time, okay? So, what's doubling time? Population is p sub naught, e to the kt. P is equal to 1,000. E to the 0.2, change it to a decimal, t. By the way, this is the formula that you would use for interest compounded continuously, okay? Which the banks could do. It'd be a pretty simple matter to do, but nobody would understand it, so they won't do that. They'd compound your interest daily, I guess. I guess it's just daily. Every day they'll do a compound interest. There's not that much difference between that and continuous anyways, but anyhow. Okay, what do we want to find out? Doubling time, so the population is now going to be 2,000. Okay. Divide by 1,000, both sides. And what this tells you is that the doubling time is the same no matter if you're going from 1,000 to 2,000, or from 2 to 4, or from 2 billion to 4 billion. Okay, doubling time is the same. You want to find out t, take the natural log. Okay. Natural log of e to the 0.2t, 0.2. Divide by 0.2. Now you got to be careful. I probably won't have this answer on the test because it's got a decimal in there. What you should do is multiply numerator and denominator by 5 to get rid of the decimal, or if you want, multiply by 10 and then simplify. In either case, you're going to get 5 natural log 2 is t. That's the answer you should have. Okay, everybody all set on that? Okay, that is radioactive decay. Okay, 11 through 13, the next section is I'm going to give you a function, and I'm going to have you set up the integral that gives the volume of the solid of revolution if it's revolved around various things. There'll be 3 questions on this. So you're going to be given some function, and I want you to just set up the integral. You don't even have to do the thing. What's that? Yes. This is going to be disks, washers, and shells. Okay? So I'm going to give you the function and some limits. And I'm going to have you revolve this around the x-axis, about the y-axis, about x equal a or x equal b. And you have to set up the integral that gives me that volume of that solid of revolution. Everything will be in terms of x, so you use this rectangle for every problem.
Is it going to be an open response or?
No, I got the integrals there. You just pick the right integral. Okay. All I have to do is set up the integral.
Can you give the equations again?
Disks,
Yeah.
volume pi, a to b, r squared dx. Washers, volume is pi, a to b, big R squared minus little r squared. And shells, okay, 2 pi RH. Okay.
So, okay, this is only the x-axis.
No, I may ask you to flip it around the y-axis, but when you take this rectangle around the y-axis, what are you going to generate? Shell. It'll give me a shell, and that's when you're going to use 2 pi RH.
Which one has to be parallel in order?
Yeah, that's it, shells. This is parallel to the y-axis. That means you're going to get a shell. If it's perpendicular, you're going to get either a disk or a washer.
Okay, so, just for, so R squared for disks, for example,
Is your function.
In this case, right here, it's our function. Almost, in every case that we do, R will be the function. Because if it's not, you'll end up with a washer. Yeah.
so whatever
Yeah.
the function be, so if it was x squared, it'd be x
X to the fourth. You're going to square.
and then you find the integral of that
Yeah.
in that way. So what about little r, big R for washer?
So if you had this same area around this line down here, say y equals -1, your big R would go from here to here. It would be your function plus 1, and you would square that. And your little r would be 1, and you'd square that to get 1. Okay? That's what you would have.
Yeah.
But again, the best thing to do is to study those tests and make sure you know those tests. And then Monday, I'll give you a test and we'll go over it. I suspect most people will be done Monday, though. That's my feeling. Okay?
So whoever's not done Monday,
Has to come in Thursday. I know it. There you go. So it could be me and you on Thursday, Trent. I don't know.
Yeah, I'll bring the Chinese food.
All right.
Dropping your lows, right?
Yeah.
So I don't have to come.
No, because the finals counts twice, man. You know what? You still may have a high enough average where you.
so
I'm not going to do that.
No, don't do that. All right, don't do
you
that.
have to get a 50.
Yeah, it'll be something like that. All right. That's 11 through 13. Then the next section. Okay, 14 through 17. Through 17. These are more integrals. But now you're going to have things like sine squared. And there'd be definite integrals. Or cosine squared. Or sine cubed. These will be integration by parts problems.
What you write over there?
Thank you.
Okay.
This is the last exam. Not yet yesterday's, the one before.
Yeah, the one before, second to last, yeah. This will be trig integrals, like I have here. Okay, integration by parts, trig integrals. Okay, that's it, though. There's only those two on this section. So I give you a couple trig integrals, and I give you an integration by parts problem. That's 14 through 17. 18 is a trig substitution problem. What is the trig sub? Okay? And hopefully you know that if you have something like x squared plus 9, x is 3 tangent. Or if you have a 9 minus x squared, x is 3 sine. Or an x squared minus 9, x is 3 secant. It would be one of those kinds of things, okay, where you have to give the trig substitution. 19 is a partial fraction problem where you have to give the sum of the constants. Okay? It'll be pretty simple. 20 is a sequence. Determine whether the sequence converges or diverges. Okay? 21 is a geometric series. Find the sum. 22 is an alternating series. 23, just a regular old series, okay? 24 is a radius of convergence. And 25 is find an error in approximation.
What do you mean by series?
This one here, I'm going to give you some series. Maybe I'll give you this. Ask it, converge or diverge. Or I'll give you,
okay.
yeah.
Diverge.
And that's it, just two answers, it's converge or diverge. What's that? 25 is find the error in approximating sine or cosine.
So 25, oh, it's not, oh, okay. It's not gonna be like a two-part?
No, it's only a one part. What it is, I say, if you're going to approximate the sine of 1 by using the first 3 non-zero terms, what's the error? So you have to find the next non-zero term.
So
Okay.
3 would be.
Yeah, let's do it. Here's the sine.
So that's the 1 over 120, right?
Yeah, well, that would be, if you use two terms, the error would be the third term. But if I say use the first 3 terms, the error is going to be x to the 7th over 7 factorial. And if x is 1, it'd be 1 over 7 factorial. That's 1 over 5,040. Okay, that would be the error.
Oh, I know you said it, but I kind of spaced out there. The 18 trig substitution, what is that specifically?
I'm going to give you a problem like this and say, what is the trig substitution that should be used in solving that problem?
X squared minus 9?
Yes. And you should know what the trig substitution is to solve that problem, to do that integral.
Something 3,
Yeah.
something x, but I don't. 3 plus x, 3 plus x, no?
What is it?
3 plus x, or minus x?
No.
No, tangent is.
Secant. Secant. X squared minus 9, u squared minus a squared, that's a secant substitution. 9 minus x squared is a sine substitution. X squared plus 9 or 9 plus x squared, that's a tangent substitution. Okay?
Oh boy.
That is your test. Nick?
The x minus x cubed. I don't know. I think it's like the sine x thing.
Yeah.
How'd you get the 5?
How'd I get what?
The 5, the plus whatever.
That's the series for sine x, the infinite
So
series.
the answer would be negative, right? Because it's minus 7x over.
No, the answer is an absolute value. It's never
Oh.
negative. That error is always positive. This is the sine series, okay?
It's all.
The Maclaurin series expansion for it. Sine being odd means we had all odd exponents, and it goes plus, minus, and divided by the factorials.
So then it'd be minus. That's where you get the.
Yeah, that would be the next one. But like I just said to Melissa, the error is always the positive. It's always a positive number. Okay, always have a positive. I'll do any problems you want to do or whatever you want to do. But you have 2 shots at this thing, for Pete's sake, Monday and Thursday. And I can't imagine it. What's that?
You want to go home?
It's up. No, Red Sox aren't even playing tonight, so the heck.
We're here till 9.
I would go home, and what would I do at home? I would go probably play chess online. So
You love chess, huh?
I play chess online all the time. I play chess here all the time. I play
What website do you play on?
chess.com. Rich28, that's me. If you can find me on there, you can challenge people.
So you lied to people that you're 28?
That's all I can know.
Yeah, no, it's not that kind of a site where you try and socialize with anybody. You play chess, and that's what you do.
I know, I actually have an account with you.
Rich 28. 28 is because 28 is my favorite number, and it's my favorite number because it's my professor number here at STCC, but it's also a perfect number. 28 is perfect because the sum of its proper divisors is equal to 28. 1 plus 2 plus 4 plus 7 plus 14 is 28. It's a perfect number.
You could have just said, that was my sports number.
What's that?
That was my sports number.
Really? So there you go. There you go. All right. Hey, I'll see you Monday.
No wonder my birthday's on the 28th.
See ya.
Я не могу тебе видео еще пока я перепишу. Let me take
Yeah, take care. Yeah, if you could do that, that'd be great because Danielle's going to need it. What do you? Oh, this. Yeah, that's.
take a picture.
Yes, good deal. Thank you.
What?
Did I stop recording? No.
You didn't stop recording?
No, I didn't.